My lecture today is about the calculation of the three-phase power, the apparent power in terms of the sequence components in the sequence networks. How to calculate the apparent power in the sequence networks. Firstly, the three-phase system, uh, three-phase system maybe is a three-phase load system. Is maybe a load system. Okay, like this. This is a load, an impedance load, a three-phase load consumed a power from a source. So as you see, we have three phases, phase A, phase B, phase C, okay? And we have three voltages, the phase voltage of A, the phase voltage of B, and the phase voltage of phase C. So we have three quantities of voltages, VA, VB, VC. And we have also three currents. Current A, phase A, IB, the current of phase B, the current of C, IC. Okay, so this is a system. This is a three-phase system. This is a three-phase impedance load system. Also, the system, the three-phase system, may be a generation system. Generation system, like this system, like this system. This is a three system. This is a generator, delivered power. So this system is supply power. This is the current in phase A. This is the current produced by the generator in phase B. This is the current produced by this generator, by this system in phase C. And also we have three voltages. This is the neutral. Voltage of the phase A. We have the voltage of phase C, voltage phase A, means that the voltage between the point A, the terminal A, and the neutral. Okay, this is the neutral. And the voltage of phase B between point B, the terminal B, and the neutral. And we have the voltage of phase C between point C and the neutral. So also in this system, the generation system, we have three quantities, VA, VB, VC. and we have three currents, IA, IB, and IC. Okay, and also maybe may, maybe the system is a fault system which has generation, okay, and transmission system and the load. All system consists of the part of the which is intended to produce power, to generate power, and the second part, the part of the transmission, and the third part is the load part. The whole system is a three-phase system, and this system also has three voltages, VA, VB, VC, and three currents, IA, IB, and IC. Okay, in these systems, always we need to calculate the apparent power, S, the apparent power, which is equal to the active power and the reactive power. Okay, for the three-phase system, S for the three-phase system equals to the P, the active power for the three-phase system, and the reactive power also for the three-phase system. So the load consumed an apparent power, S. S for the load. And the generator also produced power, S generated. And the whole system, we have a parent power. We need to calculate the power. We need to calculate the generated power. We need to calculate the consumed power. We need to calculate the transmitted power by the uh, the transmission line. Okay, so this is the subject that we need to explain how we can calculate the power, whether it is generated, whether it is consumed, whether it is transmitted, or whether it is from the generation to uh, the load. Okay. Uh, Let us erase this. Okay. This is the first point which I need to clarify, that we have a three-phase system and we need to calculate the apparent power in this system. The system may be load and the system may be a generator. Okay. How to calculate the apparent power in a three-phase system? As we said, the apparent power for the system, S of P, apparent power of the system, three-phase system, equals to the apparent power of the phase A plus the apparent power of phase B plus the apparent power of phase C. Okay, this is the general equation. This is the general form for calculation. This is the general equation, the general form to calculate the apparent power. We need to calculate the power of phase A. We need to calculate the phase power in phase B, the power in phase C, and adding up the three terms, three values to obtain the total three-phase power. This is the, and you know that the power for phase A is equal to VA multiplied by IA conjugate, while the power of phase B is equal to VB multiplied by the current, the conjugate current of phase B, plus VC multiplied by the conjugate current of the phase C. Okay. Now, this is the general form. This equation is valid for any system, whether the system is balanced, whether the system is unbalanced, whether the system is symmetrical or unsymmetrical. This is the general form. This is the general form of calculation the apparent power. Now, maybe we have a special case for the system. If the system is symmetrical, if this is a special case, okay, the general case, the system is asymmetrical. A special case is the system may be asymmetrical. The system, if the system is symmetrical, the system is symmetrical, then system is symmetrical, then the power of phase A is equal to the power of phase B equal to the power of phase C. In this case, in this special case, SP is equal to 3 by VA by IA conjugate. Actually, it is equal to 3 VB IB conjugate equal to VC IC conjugate. This is 3. Sorry. This is a special case. This is for the symmetrical system. But if the system is unsymmetrical, this equation is not correct. This is the general form. This is the general equation. This is a special case. This is the equation for the symmetrical system. Okay? You should note that VA is the phase voltage. Phase voltage. Voltage. This is VA. The voltage between the terminal A and the neutral. Okay? This value. And IA is this formula or in the First formula, first equation is the line current. IA is the line current. The current passes through the transmission line. Line current. Okay. This is a phase voltage. It is not the line-to-line voltage. If this voltage is line-to-line, then instead of 3, we multiplied by the root of 3. This is the V root of 3 multiplied by VL multiplied by IA conjugate. Okay? Should be noted whether the voltage you use is a phase voltage or it is a line-to-line voltage. If it is a line-to-line voltage, we calculate the apparent power using this formula. If you use the phase voltage, then you should be calculate using this formula. So we have three formulas, three equations. First equation for any system. The second formula for a symmetrical system using the phase voltages. The third equation is the equation for a symmetrical system using line-to-line voltages. Okay, this is the first point, how to calculate the apparent power. The next note that I want to explain, what do we mean by conjugate? The conjugate of the current. If we have a coordinates and we have this here, a vector A. Where is the conjugate of the vector A? This is the conjugate of vector. Okay. The conjugate of any vector is the picture. Suppose we have here a mirror, the vector of the phase A. This is the vector. This is the picture, sorry, of the phase, the vector, the picture of the vector A. Okay, the picture of the vector is the conjugate vector. Okay, suppose we have here a vector B. The conjugate of B is the picture of B. This is the conjugate of B. Okay, and the conjugate of this vector is B. Okay, you should understand this. And we use here the conjugate of currents. Okay, not the current, the conjugate of the current. And you see that the magnitude, the two currents, the two vectors, vector A and the conjugate of A, are equal in magnitude, but the angle is different. The angle is different. This is angle theta, and this is minus theta. Okay. Yes. The Second point, which we are going to analyze, assuming that the system we analyze the system, assuming that this system is symmetrical. We assume that our system, which we are going to make calculations, is a symmetrical system. And the practical system is a symmetrical system. So we work in a symmetrical system. Our system, the practical system, is a symmetrical system, which means that the voltages VA, VB, VC are equal in magnitude and displaced by 120 degrees. This is VA, okay? This is VB, okay? And this is VC. And the same for currents. This is the current of phase A, okay? This is the current of phase B, and this is the current of phase C, okay? The voltages for a symmetrical system are equal in magnitude and displaced by an angle of 120 degrees, okay? These angles are 120 degrees. This is the symmetrical system. And for this system, if we need to calculate the apparent power, we use this formula. In the symmetrical system, we need the voltage of phase A, we need the current of the line A, okay? Then we can calculate easily the apparent power using the formula, the equation number 2. Okay. This is the practical system. This is the system that we make our analysis, make our calculations. Okay. If this system, for example, is subjected to an unsymmetrical fault, if the symmetrical system is subjected to an unsymmetrical faults, and we know that the unsymmetrical faults, such as line to ground fault, or line to line fault, or line to ground fault, then the system becomes unsymmetrical. Then the system becomes unsymmetrical. So this is the first case. This is the first reason how the system is converted, okay, from symmetrical to unsymmetrical. If the symmetrical system is subjected to an unsymmetrical force, then the system becomes unsymmetrical. Since the system is unsymmetrical, after the fault, then we should use the equation number 1 for calculation the apparent power. For calculation the apparent power. Okay, so this is the equation we should work Okay, we should take to calculate the apparent power. This is the general form for calculation the apparent power. Okay, okay, yes. This is the, as we said, the power of phase A, the power of phase B, the power of phase C, or C. Okay, now, okay, uh, the the system, as you see, is a generation system, like the system in three-phase system, like the three-phase system of load. So if we need to calculate the apparent power of this generator, of this synchronous generator, we use the same formula, the same equation. VA, this is VA, multiplied by IA conjugate, current IA, plus VB, okay, multiplied by IB conjugate, plus IVC multiplied by IC conjugate. Okay, this is the same formula. This is the same formula we use in the load three-phase system. This is the same formula. This is the same formula. Okay, the difference that this is a load system, while this is a generation system. This is the apparent, the generated apparent power, while this is the apparent consumed power. This is the only difference between the power in the load and the power in the generator. In the generator, the power is delivered, is generated. In the load, the power is consumed. Now, the third point, how we can write this formula in a matrix form. This is the general form. How we can write this formula in a matrix form. If we want to write the equation number 1 in a matrix form, we write it as follow. Okay. VB, SB, sorry, equals to VA, EA, VB, VC. This is a raw vector multiplied by IA conjugate IB conjugate IC conjugate. Okay, this is equation number 5. This equation is the same as equation number 1. This is the same as this equation. The only difference that this equation is written in a matrix form. This is written in a matrix form. Okay, in a matrix form. And we use matrices in the power system analysis. Our all calculations are based on the matrices forms. Okay, all the equations, our equations in the power system analysis use the matrix form. The matrix form. This is, as we said, a row vector, and this is a column vector of currents, conjugate currents. Okay. The equation number 5 can be written also in this form. B. This form. VA VB VC. This is a column vector. If we want to write this vector in column vector, then we use the symbol T. T denotes the transpose. The transpose of this vector is the row vector. This is a column vector. The transpose of column vector is a row vector. Okay. So this vector is the same as this vector. This is the same. So multiplied, SP multiplied by the currents I conjugate IB conjugate IC conjugate. Okay. This is the equation number 6. What is the difference between equation number 5 and the equation number 6? There is no difference. There is no difference between the two equations. This is written in matrix form, and this is written in a matrix form also. Okay. Now, as we said, if the system is subjected to unsymmetrical force, then the system becomes unsymmetrical. How to analyze this system, how to analyze the unsymmetrical system? As we said in the previous lectures, the system is replaced by 3 systems. So the unsymmetrical system, okay, and symmetrical system is replaced by 3 systems. The zero sequence system plus the positive sequence system plus the negative system. plus the negative system, sequence system. Okay? If the system is asymmetrical, then we replace this system by three systems: the zero sequence system, the positive sequence system, and the negative sequence system. So, if the system is asymmetrical, that means VA, VB, VC are unsymmetrical, which means that they are differ by the magnitude or are they are differ by the angle, by the displacement, or the both by the magnitude and the angle. Okay, in the symmetrical system, as we said, that these vectors, the voltages and the currents, IA, IB, IC, these quantities symmetrical in symmetrical systems are equal in magnitude, and there is a displacement by 120 degrees. But if the system is unsymmetrical, if the system is subjected to unsymmetrical force, then are becomes these values become unsymmetrical, which means they are differ by the magnitude and differ by the angle. The displacement between them is differ than the 120 degrees. Okay? We assume that our system is subjected to unsymmetrical force, then our system that we should have make analysis is unsymmetrical. Then the voltages are unsymmetrical and the currents are unsymmetrical. Okay. Now, in this case, if the system is asymmetrical, if the system is subjected to unsymmetrical fault, as we said in the previous lecture, that each quantity of voltages and currents are equal to three quantities. Of voltage A, phase A, is equal to VA naught, zero sequence component, plus VA1, the positive sequence component, plus VA2, the negative sequence component. Okay? And the same for voltage B. Voltage V is equal to VB naught plus VB1 plus VB2. And the voltage of C, VC, equals to VC naught plus VC1 plus VC2. Okay? Okay? We have three systems. This system is zero sequence system. This system, VA1, VB1, VC1, is a symmetrical system. We called it positive sequence system. It has three voltages equal in magnitude and displaced by 120 degrees. And this is a negative system. Also, it is a symmetrical system. These voltages are equal in magnitude and displacement of 120 degrees. But the difference between the positive and the negative, these voltages are rotate in positive, rotate the same as the original system rotating. Okay, it rotates as these voltages rotate. Okay, while the negative system, these voltages are rotate in opposite direction, in the negative direction of the rotation of the original system. Okay, so we have three systems. Zero sequence system, there is no rotation. The positive sequence system is rotate the same as the original system, and the negative system, the rotation is negative to that of the rotation of the original system. As we explained in the previous lecture, we explain how we draw the three systems: the zero, the positive, and the. Now, to rewrite these equations in an easily manner, in an easily form, we use the operator A. Okay, the operator A. It is an important operator in a three-phase system. Okay. Now, if we have a coordinate x and y, this is a vector. Assume that this vector has a magnitude of unity. If we multiply this vector by the operator A, then the result is here. This is the operator A. This is the operator A, which means, and this angle is equal to 120 degrees. So if we multiply any vector, if we multiply any vector by the operator A, then this vector is rotate anti-clockwise by a degree of 120 degrees. Okay? Any vector multiplied by the operator A, this vector is this vector rotates anti-clockwise by 120 degrees. So, also, if we multiply the vector A by the vector A, which means we have A squared, the same concept is valid. Then we have here, this is A squared, the vector A squared, which means that A rotate anti-clockwise by 120 degrees. Okay? If we multiply A squared by A, it also A squared rotate anti-clockwise by 120 degrees. This is A to the power 3. This is A to the power 3. As you see, A to the power 3 is equal to 1. Is equal to 1. Okay. And also, as you see, we can write A in this form. The vector A is equal to 1 with an angle of 120 degrees. Okay. Okay. So this vector is, if this vector is multiplied by another vector, the magnitude of the vector is unchanged, while the direction of the vector is changed. Okay, the vector rotate anticlockwise by this value, by 120 degrees. It's clear. It's clear and easy. A is equal to 1, and the angle of has an angle of 120 degrees. This is A. As you see, the vector A has two components. This component and this component. Okay. So we can write A in the rectangular form, as you see, is equal to minus 0.5 plus J 0.866. So we have this formula of writing A, and we have this formula of writing minus 0.5 is equal to 1 multiplied by the cosine of 120 degrees. And this value, 0.866, is coming from multiplying 1 by the sine of 120 degrees. Okay? And the same for the A square. It has two components. The horizontal component, the component on the real axis, and the component in the imaginary axis. Also, we can write A square in two forms. A square equals to equals to 1, but the angle here, instead of 120 degrees, is 240 degrees. Okay? And equal, the rectangular form is equal to minus 0.5 minus J 0.66. Okay, this is for A square. It has also two forms. The first form this is the first form, and this is the second form. Okay, 1 by cosine of the angle 240 degrees is equals to minus 0.5, and 1 multiplied by the sine of 240 degrees is minus 0.866. Yes. Now, we can use the operator A to write the voltages of voltages of VA, VB, VC. So VA is equal to VA0 plus VA1 plus VA2. And VB naught is equal to VA naught. So we can write VA naught plus VB1. What is the relation between VB1 and VA1? As we see in the previous lectures, that VB1 is leading VA1 by 240 degrees. So we can write VB1 is equal to A square VA1. And the relation between VB2 and VE2, the two vectors are equal, but VB2 leads VB2 leads VA2 by 120 degrees, which means VB2 is equal to A VA2. And the same for VC. VC is equal VA1 plus, because VC naught is VA naught, because VC naught is equal to VA naught. And what is the relation between VC1 and VA1? As we see in the previous lectures, that VC1 is leading VA1 by 120 degrees, which means VC1 is equal to A VA1. And the relation between VC2 leads VA2 by 240 degrees, which means that VC2 is equal to A square V VA2. Okay. What is the difference between these equations? Let's say that this equation is equation number 7. And these equations number 8. What is the difference between the two equations, the two sets of equations? There is no difference. These equations are the same of these equations. But in this equation, the form in 8 is used. We use here the operator A. We use the operator A. Okay? So we can rewrite the equation number 8 in the matrix form. rewriting equation number 8 in a matrix form. As follows. Okay. Okay. Return to equation number 8. These sets of voltages can be written as follows in the matrix form. VA, VB, VC. This is a column vector equals to, we can see here here we have 1, 1, 1, 1, A square, A, we have here 1, A square. Then we can write like this, 1, 1, 1, 1, A square, A, 1, A square. Okay, multiply by VA naught. Let us write V naught, VA1, 1, V1, V2. Okay, V naught denotes that it is a VA naught. V1 is the same as VA1. It is clear. It is clear. And V2 is VA2. Okay. This is for the simplification. Okay. This is equation number 9. What is the difference between equation number 9 and 8? There is no difference. This equation is written, equation number 9 is written in the matrix form. Written in the matrix form. This is written in the matrix form only. Okay. Now, this matrix can be written as follows in a compact matrix form. On a compact matrix form, like this. This matrix, we can write it like this. V phase. So V phase is a column vector, VA, VB, VC. Okay? And this vector is termed by A. Okay? And this vector is termed by VS. Okay? So equation number 10 is written by a compact matrix form. Compact matrix form. Matrix form. Compact matrix form. There is no difference between equations 8, 9, 10. Only the difference by the form of writing. This is written by the compact form. Compact matrix form. Yes. Now, from this equation, from the equation number 9, we see that if we have the sequence quantities of the voltages, which means if we have V naught, V1, V2, okay, we can find the phase voltages. Okay. Now, also from equation number 9, we can write the following equation. From this, if we multiply this equation by the inverse of A, then we can write this equation. Vs is equal to inverse of A, inverse of A, inverse of A, inverse of A multiplied by V phases. Okay, this is the equation number 11. Okay, in equation number 11, we see that if we have the phase voltage, these voltages, VA, VB, VC, we can find the sequence quantities. Okay, so if we have the phase voltages, VA, VB, VC, we can find the sequence quantities, V naught, V1, V2, by using equation number 11. Okay, and also if we have the sequence quantities, we can find the phase voltages, the phase quantities, by using the equation number 10. Okay, so by means of equations 10 and 11, we can find phase voltages. Okay, we can find phase voltages also from the sequence quantity. Also, we can find Vs, the sequence quantity from the phase voltage. So we can convert the phase quantities to sequence quantities or vice versa. We can obtain from the sequence quantities the phase quantities. This is the most important note that I want to explain. We can convert the phase quantities to sequence quantities. We can work on the phase domain, and also we can work on the sequence domain. How to move, okay? How to make the transition from the phase domain to the sequence domain, we use the two equations, 10 and 11. Okay? Okay, this is the most important note that I want to explain in this lecture. So, what is the benefit of equations 10 and 11? By means of these equations, we can move, we can move from the phase quantities to the sequence quantities, or a vice versa, from the sequence quantities to the phase sequences. Also, the student must to easily use these equations. The student must know the matrix A. Okay, as you see, matrix A is equal to 1, 1, 1, 1, A square. Okay, A, 1, A, A square. Okay, this matrix is A, is called A. Okay, is denoted by A. And the second thing, what is the inverse of A? What is the inverse of the matrix A? This matrix. This matrix. The inverse of A is equal to 1 to 3 divided by 3, 1 divided by 3, 1, 1, 1, 1, A square, 1, A square, A. Okay? These things should be understood by the student. The student must remember this. What is the value of A and what is the value of inverse of A? In order to use the equations 10 and 11, in order to replace the sequence quantities by phase quantities, or to replace the phase quantities by sequence quantities. Okay? Because in the unsymmetrical system, the first step, we replace this system by three systems. So we are going to do our analysis in the sequence domain. We use the sequence quantities of voltages and of currents. Okay? The same thing as we write the equations for the currents, we can also write these equations for currents in the same manner, in the same form. Okay? For currents, system is unsymmetrical, so we have three currents, IA and IB and IC. Okay, and these currents are differ in magnitude, are in magnitude, are differ in magnitude and differ uh, in the angle. Okay, so IA also is equal to IA naught Z plus IA1 plus IA2. Okay, and the same concept, IB is equal to IA naught, because IB naught is equal to I naught, plus A square I A1 plus A I A2. And the same for the current C. IC is equal to A naught plus A I A1 plus A square I A2. All these equations from 1 to 11, even the equations for the currents are written in the previous lectures. So the students may return to these lectures and see how these equations are written. Also, only in this lecture, I want to explain these equations, to explain these equations to be understood by the students. So also we can write these equations in phase domain like this, IA, okay? IA, IB, IC is equal to, as you see, equal to 1, 1, 1, 1, A square, A, 1, A square multiplied by I0, which is IA0, I0, I1, 0, I2. Okay, this is the first form in matrix form. And also we can write it in compact matrix form like this. I phase, the phase quantities of the currents is equal to matrix A multiplied by I sequences, the sequence quantities of the currents. Okay, this is equation number 12. Okay, and the same, we can write that IS, the sequence quantities of the currents, is equal to inverse of A multiplied by I phases. Okay, this is equation number 13. Okay, so we have also two more equations, equation number 12 and equation number 13, that enable us to convert the phase quantities to sequence quantities. Okay, to sequence or vice versa, to convert the sequence quantities to phase quantities. Okay, this is an important note that I want to explain. So, as a summary in this lecture, we explain how to convert the phase quantities to sequence quantities and how to convert the sequence quantity to phase quantities by using, as we said, the equations number 10, number 11, and number 12, and number 30. The last note that I want to explain. Suppose we assume that we need to calculate I naught, the zero sequence current of the system. How we can calculate the zero sequence current of any system. And this is important, very important. Okay. Now, from equations, equation from number 13, we see that I naught, I naught is equal to, from this equation, is equal to 1 divided by 3 of I A plus I B plus I C. Okay, I C. I see. Now, if I ask the following question, if I need to calculate the neutral current, how can I calculate the neutral current? The neutral current, as you know, is equal to IA plus IB plus IC. Okay, so this term is the neutral current, is the neutral current. So we can write that the zero sequence current is equal to 1 divided by 3 of IN, okay? Or the neutral current is equal to 3 I naught. This is an important note that the student must know. Okay? Now, suppose we have a system. We have a system, three-phase system, three-phase system. As we said, this system may be symmetrical. Okay. And in general, the system is unsymmetrical. Okay. If the system is symmetrical, then IA plus IB plus IC is equal to 0. Okay. So for the symmetrical system, I0 is equal to 0 for the system, the symmetrical system. I naught is equal to 0. Now, for the unsymmetrical system, okay, we have two cases. We have two cases. The first case, maybe the system has no neutral conductor. Okay, so the unsymmetrical system, the first case, there is no neutral conductor. There is no neutral. In this case, also I note the zero sequence current is equal to zero. Okay, no neutral, or it may be the system is delta connected. System is delta connected system. Then there is no neutral conductor. Also in this case, the I naught is equal to zero. Okay. And the second case, the system has a neutral. If it has a neutral, then I naught not equal to zero. There is a value of the system, of the zero sequence. This is a very important note. So as you see, I naught in general, in general, uh, in general, may explain, may show us the case of the system, okay, the situation of the system, or may it tell us whether the system is symmetrical. If the system, if the zero sequence current is zero, there is two options. The system is symmetrical, or the second option, there is no conductor, there is no neutral conductor in the system. In the two cases, the zero sequence current is zero. In the two cases, this is the first case, and this is the second case. When the zero sequence current is equal to zero. The first case, maybe the system is symmetrical, and the second case, the system has no conductor. Also, the zero sequence current is also. Otherwise, I naught as a value, okay? I want to finish the lecture. I want to finish this lecture, and I want to say goodbye to everyone. We will wait you to the second lecture. Goodbye. Assalamu alaikum wa rahmatullahi wa barakatuh.